Hello and welcome to our presentation on hydrogen technology and the processes involved in its generation, compression and storage. Hydrogen has incredible potential as a clean and versatile energy fuel. When consumed, it only produces water, making it an environmentally friendly choice for a sustainable energy future. This fuel can be generated from natural gas, nuclear power, renewable power and biomass. Its versatility opens up possibilities for application in transportation and electricity generation. Hydrogen is also the simplest and most abundant element, consisting of just one proton and one electron. This contributes to its high efficiency and almost zero emissions. The potential impact on reducing greenhouse gas emissions is tremendous, offering a viable solution to address the environmental challenges. When applied to highway vehicles, hydrogen can lead to a substantial reduction in emissions. Studies show that these vehicles could achieve an impressive 50 to 90% reduction compared to today's gasoline vehicles. For hydrogen to play a pivotal role in transportation and electricity creation, it must be economically competitive compared to other fuel sources. Currently, this translates to a benchmark of being priced of at least $4 per gallon of gasoline. Our presentation delves deep into hydrogen generation, compression, and high-density storage, shedding light on the pivotal factors that drive the development and integration of hydrogen as a viable energy solution. Hydrogen, with its various production methods, poses unique challenges such as those encountered in steam methane reforming. Following production, the next critical step involves compression for efficient storage and transportation. It is through the compression process that hydrogen becomes economically feasible for transportation and storage. Moreover, we explore the crucial aspect of storing hydrogen at high densities, maximizing its energy density and ensuring practical applications in various sectors. Different strategies are being developed to provide a safer and more efficient storage option, addressing concerns and enhancing the overall viability of hydrogen as an energy carrier. The very first process is steam methane reforming. In this method, methane from natural gas undergoes a reaction under the influence of steam at 3 to 25 bar pressure, and with the aid of a catalyst, a synthetic fuel is created. This fuel is a mix of carbon monoxide, carbon dioxide, and hydrogen. This reaction is endothermic, requiring the input of heat, as seen in the equation on the left. The process is crucial for hydrogen generation, yielding the highest purity form of hydrogen. The purity makes it not only cost-effective but also versatile for the use in industrial processes and fuel cells. There's also another method called partial oxidation, where methane reacts with oxygen as seen in the equation on the right. In this exothermic reaction, carbon monoxide is produced, releasing heat. While the process is faster than steam reforming, it falls short in generating sufficient hydrogen for our needs. To further refine the hydrogen output and eliminate carbon monoxide, we employ the water-gas shift reaction. This transformative process yields carbon dioxide and additional hydrogen. As we progress into hydrogen production, a final step known as pressure swing adsorption is used. This focuses on the purification of hydrogen by removing carbon dioxide and other impurities using a gas stream. The result is pure hydrogen. This causes carbon dioxide and impurities to adhere to an adsorbent bed, allowing everything else to pass through. The success of this purification relies on precise control of temperature and pressure. While hydrogen in itself is an emission-free fuel, it's important to acknowledge that the feedstock used in its production is derived from natural gas, contributing to greenhouse gas emissions. Feedstock refers to the raw materials fed into a process for conversion. The escalating prices of oil, coupled with anticipated shortages, have further underscored the importance of natural gas in this context. Moreover, burning natural gas exhibits lower carbon emissions compared to other fossil fuels. Notably, it isn't subject to the constraints of weather conditions or seasons, setting it apart from some conventional energy sources. Let's delve into the concept of energy centers, a strategic approach that holds immense potential for transforming urban energy landscapes. The establishment of steam methane reforming facilities within or in close proximity to urban centers presents several key advantages. The first one being SMR facilities. By situating SMR facilities near urban centers, we reduce the need for extensive energy transportation, minimizing losses and enhancing overall efficiency. The next factor is grid support. Hydrogen generated through SMR can integrate into existing natural gas pipelines, offering a versatile pathway for energy storage and grid support during peak demand. SMR-produced hydrogen emerges as a crucial transition fuel, aiding urban areas in reducing reliance on fossil fuels and mitigating overall carbon emissions. It can also synergize with power-to-gas technologies, enabling excess renewable energy to be converted into hydrogen for later use, promoting sustainability. Finally, government support and regulations play a crucial role in driving the transition to hydrogen-based urban energy systems. Governments can play a proactive role by offering financial incentives and regulatory support, fostering the development of SMR facilities and widespread absorption of hydrogen technologies in urban areas. Enforcing emission standards helps get cleaner energy sources, making SMR with carbon capture more attractive and aligning with sustainability goals. In summary, the integration of steam methane reforming coupled with carbon capture and storage technologies holds the promise of establishing vibrant urban energy centers. These centers not only address the energy needs of densely populated areas, but also contribute significantly to a more sustainable and low carbon energy future. However, the success of this hinges on the consideration of environmental and economic and social factors, necessitating collaboration with diverse stakeholders.
Electrolysis stands as a cornerstone in the clean energy paradigm, utilizing electrical energy to drive the chemical separation of water into its elemental components. Let us unravel the well-known principle behind water electrolysis, a process fundamental to the production of oxygen and hydrogen gas. The heart of an electrolysis unit is an electrochemical cell, seen here, where water is decomposed into hydrogen and oxygen gases. The process involves two electrodes connected to an external power supply, initiating the production of hydrogen at the cathode and oxygen at the anode. The transformative journey begins when a specific voltage is applied across these electrodes. The theoretical minimum voltage required for water electrolysis, termed the thermoneutral potential, is around 1.23 volts, but the actual one is believed to be 1.48 volts. This critical step sets in motion the production of hydrogen gas at the negatively biased electrode and oxygen gas at the positively biased electrode. It's crucial to note that the electrolysis of water is not a spontaneous phenomenon. The standard global reaction potential is negative, necessitating an external power supply to drive the reaction forward. Alkaline electrolysis, with roots dating back to 1902, is esteemed for its reliability, safety, and longevity, boasting lifetimes of up to 15 years. In this process, the cathode reduction of alkaline solution produces hydrogen and hydroxyl ions. Eliminating the hydrogen, the remaining hydroxyl ions travels through an electric circuit to the anode side, generating oxygen and water, as shown in the figure on the left. Operating efficiently between 5 degrees Celsius and 100 and up to 448 bars, alkaline electrolyzers are favored for large-scale hydrogen production due to their simplicity and robustness. In contrast, as you can see here on the right, the proton exchange membrane electrolyzes utilizing ion exchange polymers and gas-tight membranes. Despite lower production capacities than alkaline counterparts, the PEM electrolyzers excel in responsiveness and high-purity hydrogen generation. PEM water electrolysis involves the electrochemical split of water into hydrogen and oxygen with protons H+ and electrons, and a proton conducting membrane. The basic principle of PEM water electrolysis is shown. Despite higher costs and shorter lifetimes, PEM electrolyzers are prized for swift responses to varying power inputs, operating efficiently at higher current densities, and delivering high-purity hydrogen, making them valuable in precision-demanding applications. The key distinction lies in the ions diffusing between the anode and cathode sides. Alkaline electrolysis involves hydroxyl ions, while PEM electrolysis involves protons, H+ ions. The pivotal factor in achieving emission-free hydrogen lies in the energy source, emphasizing the imperative shift to renewables. The cost dynamics of renewable energy further underscore this transition, with solar and wind emerging as the cost-effective options, promoting a future of greater affordability. Various projects exemplify the seamless integration of electrolysis with diverse renewable sources, showcasing the adaptability and advancing the vision of clean hydrogen production. For example, the Wind-to-Hydrogen project in the US uses wind turbines to power electrolyzers, producing green hydrogen. In Germany, the solar Wasserstoff Bayern project integrates photovoltaic panels for solar-powered electrolysis. Hydropower linked electrolysis diverts excess energy from hydropower plants to produce hydrogen, highlighting adaptability to intermittent sources. Geothermal power electrolysis, demonstrated by researchers, offers efficiency and cost effectiveness. Hybrid approaches like the Sotavento wind farm in Spain integrate alkaline electrolysis with wind energy, emphasizing versatility. These examples collectively underscore electrolysis as a key player in synergizing with diverse renewables for sustainable hydrogen production. The solar Wasserstoff Bayern project, for instance, demonstrates the integration of photovoltaic panels, water electrolysis, and hydrogen storage in fuel cells, showcasing the practicality of green hydrogen in comprehensive solar hydrogen power systems. Driven by a commitment to a zero-emission future, green hydrogen production fueled by renewable energy emerges as a tangible solution for smart cities. Its significance is undeniable in the broader energy transition, addressing climate change challenges with zero greenhouse gas emissions. As global initiatives including the European Green Deal prioritize clean hydrogen, the installation of electrolyzers powered by renewable energy is set to increase, meeting the rising demand for renewable hydrogen in transportation, heating, power generation, and industry. Looking ahead to 2030, the goal is to scale up renewable hydrogen production to 40 gigawatts of capacity, aligning with the evolving needs of smart cities. Green hydrogen, with its potential to reshape the energy landscape, is poised to play a pivotal role in achieving a sustainable, decarbonized future for smart cities worldwide. Biomass, derived from diverse organic sources, plays a pivotal role in sustainable energy applications. Agriculture biomass, encompassing crop residues like corn stalks, provides energy without competing with food production. Lignocellulose biomass emphasizes sustainable forest resource utilization, including wood and plant matter. Dedicating energy crops, such as switchgrass, contribute to the biomass production, while algae biomass, derived from microorganisms like microalgae, holds promise for biofuel and hydrogen production. In the context of hydrogen production, biomass serves as a substrate in various biological processes. Dark fermentation, driven by anaerobic bacteria on carbohydrate-rich substrates, operates independently of light. The integration of dark and photofermentation enables continuous hydrogen production, with algae like Chlamydomonas reinhardti utilizing direct biophotolysis to convert solar energy into hydrogen. Cyanobacteria, in indirect biophotolysis, enhance hydrogen production through mutant strains and CO2 fixation. Photofermentation by purple non-surfal bacteria overcomes oxygen inhibition, although challenges include limited organic acid availability. Biocatalyzed electrolysis presents an alternative, oxidizing acetate or dark fermentation effluent to produce hydrogen with electrical energy input. This multifaceted use of biomass contributes to a more sustainable and circular economy. One of the foremost advantages of biomass-based hydrogen production lies in renewable nature. Algae and biomass-derived substrates are abundant and can be sustainably sourced, providing a continuous and eco-friendly feedstock for hydrogen generation. Unlike fossil fuels, biomass is not finite and can be cultivated, mitigating concerns related to resource depletion. This renewable aspect aligns with broader efforts to transition towards sustainable energy sources. Furthermore, utilization of biomass, including waste materials, contributes to effective waste management. Biomass-based hydrogen production not only taps into renewable resources but also addresses environmental concerns by repurposing organic matter. The potential for carbon neutrality is another significant advantage, as biomass processes, when managed responsibly, can be designed to balance carbon emissions, minimizing the overall environmental impact. In essence, biomass-based hydrogen production stands as a promising and sustainable pathway, intertwining renewable resource utilization with environmentally conscious energy practices.
Transitioning from the generation of hydrogen, we move on to the crucial step of hydrogen compression. Hydrogen, in its gaseous form, has a low energy density, meaning it occupies a large volume compared to its energy content. This is where compression steps in. It's a crucial process that reduces the volume of hydrogen, making it practical for storage, transportation, and utilization. Hydrogen compression is the bridge between production and application and allows us to store and transport hydrogen efficiently, overcoming the limitation associated with its low density. Now, the compression methods can be split into two categories: mechanical and non-mechanical compression. Our focus will be directed towards exploring these compression methods with a more detailed examination of piston compressors, diaphragm compressors, and electrochemical compressors, which are highlighted in the image. Mechanical compressors operate through mechanical movements and rotating elements to compress gases. In reciprocating compressors, a piston cylinder engagement creates a vacuum during backward movement and compresses gas during forward movement. Examples include piston and diaphragm compressors. Rotary screw compressors use intermeshing helical screws to gradually compress gas, while centrifugal compressors employ a rotating impeller to accelerate and pressurize gas. Non-mechanical compressors, on the other hand, like electrochemical, hydride, and cryogenic compressors, don't rely on traditional mechanical components. Electrochemical compressors use electrochemical reactions. Hydride compressors utilize metal hydrides for absorption and desorption, and cryogenic compressors achieve compression through cooling and liquefaction. Each type suits different application based on factors like pressure requirements, efficiency, and environmental considerations. Reciprocating piston compressors, especially the oil-free type, are widely employed in hydrogen applications for pressures exceeding 3 megapascals. These compressors are suitable for moderate flow and high pressure scenarios, with power consumptions up to 11.2 megawatts and hydrogen flow rates reaching 890 kilograms per hour at a discharge pressure of 25 megapascals. The basic design involves a piston cylinder system with intake and delivery valves, converting rotary motion to reciprocating motion. Gas intake occurs as the piston moves towards the top dead center, followed by compression and discharge when reaching the desired pressure. Multi-stage configurations achieve higher pressures, commonly used in on-site hydrogen refueling stations. Despite challenges like embrittlement and efficiency limitations for high flow rates, ongoing developments including non-metallic materials and continuous monitoring systems aim to enhance the performance and reliability of these compressors in hydrogen applications. A diaphragm compressor operates by utilizing a flexible metal membrane known as the diaphragm to isolate the gas from the mechanical components of the compressor. This three-part diaphragm includes a process plate on the gas side, a hydraulic plate on the oil side, and a middle plate for leak detection and prevention of diaphragm failure. Hydraulic fluid, often oil, is employed to transmit motion from the mechanical components to the diaphragm, controlling its movement. The compression process involves the diaphragm reducing the volume in the cavity space, leading to an increase in gas pressure. Oil pressure control is crucial post-gas discharge to prevent excessive pressure differentials. Material selection for the diaphragm is critical to ensure corrosion resistance and durability. The closed-loop hydrogen circuit minimizes leakages, maintaining high gas purity. Despite challenges like mechanical stresses, flow rates, and durability, ongoing efforts focus on optimizing diaphragm design for the enhanced efficiency and reliability in compressing gases, particularly in hydrogen applications. Electrochemical hydrogen compressors are innovative devices with high recovery ratios of up to 95%. Operating like proton exchange membrane fuel cells, they split low-pressure hydrogen into protons and electrons at the anode. Protons move through a solid polymer electrolyte, while electrons flow through an external circuit. At the cathode, electrons and protons recombine, increasing pressure. Challenges arise at high pressures due to hydrogen permeation, but multi-stack configurations enable pressures of up to 100 megapascals. Electrochemical compressors offer advantages like low energy consumption and vibration-free operation, finding use in hybrid systems and application requiring high-purity hydrogen flows. From the methods discussed, electrochemical compressors stand out as a promising solution. These devices, operating seamlessly without moving parts, offer high efficiency and vibration-free operations. The compact design and potential for distributed storage aligns well with the integrated storage solutions needed in urban environments. Moreover, the ability to reach high pressures of up to 100 megapascals makes electrochemical compressors suitable for diverse applications within smart cities. Looking towards the future, the integration of electrochemical compressors into urban landscapes align well with the smart city vision by ensuring efficient hydrogen distribution, reducing emissions in public transportation, and contributing to the sustainability of last mile services. As cities aim for resilience and sustainability, electrochemical compressors represent a forward-looking technology that supports the broader goal of realizing smart and green cities for a more environmentally conscious and technologically advanced future.
Moving on to hydrogen storage, in order to achieve the implementation of hydrogen as part of smart city goals, storage is one of the key factors in making sure that hydrogen can be safely transported and stored for everyday usage and accessibility. Generally, there are 4 types of hydrogen storage. First is by physical adsorption, chemical absorption, gas storage, and underground storage. Physical adsorption is one of the breakthroughs of hydrogen storage. It is a promising solution in making hydrogen storage safe and convenient, especially when using it for commercial purposes. Physical adsorption of hydrogen works by adsorbing hydrogen molecules to the surface of the adsorbent materials. The van der Waals force created between the hydrogen and adsorbent are relatively weak, making it a reversible process. Some examples of adsorbent materials include activated carbon and metal organic framework, which you can see from the slide. One of the challenges of this method is that it requires high surface area of the material, and manufacturing could be very expensive and requires high energy. However, as the technology improves and matures, it has huge potentials in providing an efficient way of storing hydrogen. This could also help in distributed power sources and decentralizing power grids for a particular city. Next is chemical absorption of hydrogen for storage. This process of storage requires a chemical bonding between hydrogen atoms into compatible materials, and there are 3 general types of chemical absorption, which is liquid organic hydrogen carriers or LOHC, metal hydrides, and chemical hydrides. Liquid organic hydrogen carriers or LOHC is a method where waste fuels from biomass is used as a medium for the hydrogen molecules to be absorbed into. The process requires catalysts to speed up the hydrogenation and dehydrogenation process. This storage method offers many benefits such as high energy storage capacity and can be stored for longer periods under ambient conditions. However, the limitations such as limited catalysts and high temperature for dehydrogenation prevents it from being used widely, especially for a smart city due to safety concerns and demanding amount of energy for operation. Metal hydrides uses metal to form hydrides between the lattice framework of the metal and hydrogen atoms. It offers high volumetric storage for hydrogen and is one of the safer options for storage. The downside is that it is less efficient during the process of hydrogenation and dehydrogenation, particularly due to its slow kinetics of absorbing and deabsorbing hydrogen atoms. This form of storage can be useful for static applications, particularly to power up buildings, and etc. for a smart city due to metal hydrides being heavy. Chemical hydrides uses chemical elements such as boron to form chemical bonds with hydrogen atoms for it to be stored. The process is reversible and can be sped up by using catalysts. It also offers high volumetric hydrogen capacity, with some chemical hydrides able to safely store hydrogen at ambient pressure and temperature. The drawbacks of this storage are its high manufacturing costs and high sensitivity to impurities, which can reduce storage capacity and efficiency of the whole storage system. Finally is gas cylinder. Gas cylinders are one of the most typical and established ways of storing hydrogen. The process is direct compared to the others, where hydrogen gas is compressed into a high-pressure tank for storage. There are several compressed hydrogen tanks available, consisting of Type 1, Type 2, Type 3, and Type 4. This differs by the material it is made of, and each type has different pressure that it can withstand. Type 1 is usually avoided due to the risk of hydrogen embittlement. However, it is the most cheapest among others. Type 2 and Type 3 on the other hand are similar, with the difference being the coverage of carbon fibers surrounding the metal liner, with Type 2 only covering the middle part and Type 3 is fully covered from top to bottom. Type 4 consists of a polymer liner with a full carbon fiber outer wrapping, making it the lightest among the other types of cylinders. This is suitable for transportation and can be implemented into public buses, taxis, and even private vehicles for a hydrogen smart city. Type 2 and Type 3 on the other hand are more suited for industrial, domestic, and commercial purposes due to the weight and footprint of the cylinder.
Furthermore, underground storage methods such as salt caverns and depleted natural gas reservoirs have gained interest over recent years due to their capacity to store high-pressure hydrogen. So what are they and how are they formed? Well, salt caverns, as the name states, essentially are cavities within underground salt deposits. The way these are created is by solution mining. This process involves injecting water into deep underground salt deposits, usually more than 1,000 meters deep. Then, the surrounding salt dissolves the water, and the remaining solution is extracted using pumps, resulting in the cavity being left behind, as shown in the diagram on the right. Similarly, other potential underground hydrogen storage sites are depleted natural gas reservoirs. These sites are out-of-commission gas fields, typically consisting of porous rock formations. So how are they created? Well, the process is quite simple. First, an existing natural gas is extracted from the ground via withdrawal wells. Then, the hydrogen is injected via injection wells as a replacement, and its operational integrity is then measured using observation wells throughout the lifespan of the reservoir. So, why are these sites potential sites of high-pressure hydrogen storage? Well, this is because of their key advantages in terms of safety and capacity. Due to the physiochemical properties of rock formations, these sites have great infrastructure stability, reducing the risk of subsidence, thus ensuring long-term storage safety. Additionally, the technology for creating and maintaining caverns is well established, further enhancing the safety profile of these storage solutions. Moving on to capacity, one of the strengths of underground storage is its flexibility. Storage size can be tailored to meet specific volume requirements, providing a scalable solution. The numbers speak for themselves. Salt caverns can accommodate a substantial 2,520 tons, while natural gas reservoirs 1,000 tons. This scalability is particularly crucial in meeting the evolving and growing energy needs in the transitions into smart cities. Now, let's address some limitations. It's important to consider the geological characteristics that make a location suitable for underground storage. This, in effect, limits the long-term scalability of these storage systems in certain geographies. Furthermore, especially natural gas reservoirs, hydrogen leakage poses a problem. This is because, unlike methane, hydrogen has a higher diffusion rate. Thus, reservoirs which were once tailored to methane storage may prove less effective for hydrogen. This, in effect, requires an additional cushion gas to ensure high pressure stability and thus increases operational costs. Overall, underground high pressure hydrogen storage presents compelling advantages, from safety and capacity to the efficient use of infrastructure. While we navigate some limitations, especially in terms of economic feasibility, the potential benefits for smart cities are significant. As such, continued research collaboration and advancements in technology will be key to addressing challenges and ensuring the successful integration of these storage solutions in our pursuit of sustainable and resilient energy systems. In conclusion, the use of hydrogen as an energy carrier presents a promising and versatile solution for powering smart cities, offering an alternative to traditional energy sources. Hydrogen's potential to decarbonize various sectors, enhance energy security, and contribute to the transition to a greener future cannot be overstated. As we strive to build a smarter, more sustainable urban environment, hydrogen emerges as a critical player in the energy landscape. Its ability to integrate seamlessly with existing infrastructure, coupled with advancements in generation, compression, and storage technologies, positions hydrogen as a catalyst for innovation and progress. However, it's important to acknowledge the challenges and continue research and development efforts to improve efficiency, reduce costs, and address safety concerns associated with hydrogen utilization. Collaborative efforts between industries, governments, and research institutions will be instrumental in realizing the full potential of hydrogen in shaping the energy landscape for smart cities. As we envision a future powered by clean and sustainable energy, Hydrogen stands at the forefront, ready to play a pivotal role in the evolution of smart cities. Let us embrace the opportunities that hydrogen presents, working together to create a more resilient, efficient, and environmentally conscious urban environment. The journey towards a hydrogen-based future is an exciting one, and it's up to us to pave the way for a brighter, more sustainable tomorrow. Thank you for listening.